So today we're joined by Ashna Subramanium, who's a PhD candidate, soon to be Dr. Ashna, and in Benno Nigg's lab. And today she's going to be talking about some of the work that she's done in her PhD dissertation. So Ashna started her educational career here at the University of Calgary in 2015, and she completed a Bachelor of Science in biomechanics and kinesiology, and her research project examined the effects of shoe upper construction on mechanical ankle joint work during lateral shuffle movements. She then continued on with kind of that research area with Dr. Benno Nigg in a master's thesis, but then she fast-tracked to the PhD program in 2021. And she's planning on defending her dissertation in a little bit over a month in July.
July.
The topic is the effects of advanced footwear technology on running mechanics and performance, which she's going to be talking a bit about today. And a fun fact about Ashna is that she is a former Dinos athlete, and she played tennis and is now a coach. And she's also said on here that she's always up for a beer. So take her up on that one. And I'll hand it over to Ashna.
Thank you. Is everyone able to hear me well? Okay, perfect. The past few years, if you walk into a footwear store and you want to buy running shoes, you head over to that section, and the shoes that you're going to see in that section are going to look probably a lot like the ones on the screen here. These shoes have become very popular over the past 5-6 years, and they're specifically called advanced footwear technology, or AFTs. These are defined as performance enhancing footwear technology that combines lightweight, resilient foams with rigid moderators and pronounced rocker profiles in the sole. And a rigid moderator just means any sort of stiffening element like a curved carbon fiber plate or carbon rods that we're seeing emerge now in footwear research as well. A very popular example of an AFT that probably a lot of us in this room are familiar with is the Nike Vaporfly 4% shoe, which has a thick midsole made of a PEBA foam and a curved carbon fiber plate that's embedded between two pieces of the foam midsole. And these features together combine to make a substantial toe spring, or that forefoot curvature in the shoe. The shoe gained a lot of popularity when the study by Hookhammer and co-authors came out in 2018 and showed that the Nike Vaporfly 4% reduces the energetic cost of running by 4%, as the name suggests, across a range of different running speeds when compared to two other shoes on the market. Not only are the results of this shoe really impressive in lab tests, but also in real-world race settings. An example of this was the Breaking 2 race, which happened in 2019, in which Eliud Kipchoge broke the 2-hour world record by running the marathon in 1 hour, 59 minutes, and 40 seconds, and he wore the Vaporflies in this race. Since the Vaporfly, a lot of research has taken place in footwear science, and a lot of these studies have started comparing shoes, or AFTs, to previously established traditional shoes and looking at the energetic cost of running in the different footwear. This is just one example that looked at the energetic cost of running in marathon racing shoes. Another study that looked at the effects of highly cushioned and resilient racing shoes on running economy at slower speeds. Another study that looked at the metabolic cost of level uphill, downhill running in similar shoes. And these are just 3 examples, but one trend that pops out of these 3 studies is that people are looking at the metabolic cost of running economy in different shoe conditions, which is an indicator of how much energetic cost is required to run in these shoes. There are a few problems with this approach. When studies only look at the energetic cost of running, or looking at how these shoes improve performance without including biomechanical variables, you're unable to explain the performance improvements that are observed in the studies. They also look at a bunch of shoes that differ in different factors than just one aspect. And these are 4 examples on the slide here. And just by looking at them, you can tell that it's not just one feature that these are different in. So when different studies compare different kinds of footwear, they obviously find conflicting results. I might have different results, and if Philip does the same study, he might get something different because he used a different shoe in it. It is making it tough to control and generalize these results in the future. Recently, studies have started going back to the approach of systematically affecting specific or isolated features, like this study by Zach Behrens here last year when he defended his PhD thesis. He looked at the effect of modifying the midsole thickness on the energy cost of running. He found that the midsole thickness did not affect energy cost when you went from 35 all the way up to 50 millimeters in midsole thickness, which is actually really surprising because everyone was speculating when these shoes came out that it's the thick midsole that has everything to do with the performance improvements. So far that World Athletics, in fact, regulated how much thickness you can have to like 38 to 40 millimeters, but this shows that it really doesn't make a difference. In fact, they also found that ankle eversion was increased in shoes once you increase the midsole thickness for specifically the female population here. But that suggests that increasing the midsole thickness not only doesn't improve performance, but could also be detrimental for running. And so when we look at specific features by isolating them, we can understand whether they improve performance, whether we should include them in our shoes, and how they're improving the performance. That study looked at the effect of the thickness of a midsole, but the PIBA foam curved carbon fiber plate and the substantial toe spring in the Nike Vaporfly are still unexplored. So the overarching objective of my thesis was to investigate the isolated effects of advanced footwear technology features on running energetics, while also exploring potential underlying mechanisms that drive these improvements. And specifically, I was interested in looking at the effects of the curved carbon fiber plate and the PIBA midsole on the energetic cost of running and muscle activation, on the teeter-totter effect, and lower limb joint work. Study 1 was focused on understanding the effects of the curved carbon fiber plate and PIBA midsole on the energy cost of running to first understand whether these isolated features actually improve running performance or lower the energetic cost of running or not. And if they do, then by how much? And we decided to include muscle activation in this study because previous studies have shown that muscle activation and force production, if increased, can lead to an increase in muscle energy cost as well as increased energy expenditure during the task. And if we just think about running and the triceps surae muscle group, that account for about 25 to 40% of whole body metabolic energy cost, it seems obvious or almost logical to think that something in these shoes is reducing the amount of muscle activation you require to run and perform that task. A study recently looked at this while comparing an AFT to a traditional shoe, so not as controlled, but still looked at what happens at the muscle activation level in terms of performing running tasks over ground. And what they found is that there's lower activation of the gastrocnemius medialis muscle during the push-off phase, but they did not include metabolic measurements in this case. And so it's hard to understand whether these reductions actually led to improvements in energy cost. So keeping all of that in mind, we hypothesized for this first study that by removing the curved carbon fiber plate and replacing the PIBA foam in the Nike Vaporfly with an EVA, we would increase the energetic cost of running, and that we would also see an increase in muscle activation by changing these two features. To test this, we recruited 15 male runners that could do 10 kilometers in under 44 minutes, had no lower limb injuries, and could fit into shoe sizes US 9 or 10. And we had them perform a baseline test to determine their speed at lactate thresholds, which we found was about 4.3 meters per second. Once we determined that speed, we had them come in another day to perform the test in the different shoe conditions at 90% of their speed at lactate threshold, which was around 3.9 meters per second. And we followed the Hukamer proposed protocol for measuring energetic cost of running, where you randomize and mirror the shoe conditions. So each participant performs the same shoe condition in 2 trials by going A, B, C, C, B, A. And then we average the 2 trials for each shoe condition to have our outcome measures. The first shoe condition we tested was the Nike Vaporfly 4% shoe, intact, just how it comes when you buy it from the store. For our second condition, which was the no plate condition, we simply removed the curved carbon fiber plate from the midsole. I say simply, but it was not simple. So we just removed that plate from the midsole, keeping everything else the same in the shoe. And then we made an EVA condition where that black piece you see in the midsole is actually the new EVA that was that the PIBA was replaced with, and we kept the same profile and curvature plate in the midsole. We measured metabolic cart data using COSMED and then surface EMG using the DELSIS system, and we wanted to look at the energy cost of running and the intensity of muscle activation. Before we dive into the results, we wanted to look at whether we were able to make the shoe modifications and elicit changes that we expected from these modifications. So first, we started with an MTP 3-point bending test to compare our original shoe condition and the no plate condition. And we did see that we affected the bending stiffness as well as the energy return that you get from bending the MTP joint by about 8%. For the EVA condition, we wanted to test whether we affected the compressive energy return, and we did find that there was 10% less compressive energy return from the EVA condition compared to the PIBA foam. So we affected the shoes, but did we affect energy cost of running? This here is a plot that shows the energy cost of running on the y-axis here and the 3 shoe conditions on the x-axis. So you'll notice that the original is in the middle, and for this one subject that is shown as an example here, that is the lowest shoe condition, and they increase the energy cost of running in the EVA as well as the no plate. We see the same trend when we plot all 15 of our participants and the average in the solid black line in the middle. These changes were about 1.87% when we went from original to no plate and 2.2% when we went to the EVA condition, and they were both statistically significant. Now we've affected the shoes, the energy cost, but what's going on at the muscle level? Are we seeing the same changes there? And if we see this graph, we would expect that most of these participants are increasing their muscle activation when we go into the no plate or the EVA condition. I forgot to mention this, but we measured the muscle activation for the soleus and the gastrocnemius medialis muscles. So we start by looking at the soleus intensity in percent difference on the y-axis here, always calculated relative to the original shoe condition. So if you're seeing people in the top half of that graph, that means they increased the muscle activation from the original to the no plate, or decreased if they're in the bottom half. The middle band there in red just shows the error, and so anyone that falls into that had potentially no change. And so what we're seeing here when we go from original to no plate in the soleus is that people go up, down, and have no change. So the results are all over the place. And it's the same thing when we go to the EVA condition for this muscle. We can change the muscle and the same story still exists, where muscle activation adaptations are not consistent and specifically not consistent with what's going on in the energy cost of running. So we summarized from this first study that the curved carbon fiber plate and PIBA midsole foam reduced the energy cost of running by 1.8 and 2.23% respectively, and that muscle activation from surface EMG did not explain the improvements in the energy cost. So what is going on? There has to be something else that is a potential underlying mechanism for these improvements. So we move to study 2. We look at a teeter-totter mechanism that was previously proposed by Dr. Nig in 2020, where the authors suggested that the unique design of an advanced footwear technology shoe creates a class 1 lever mechanism that allows it to act like a teeter-totter. And what that simply means is that you apply a force to the front part of the MTP joint, which acts as a fulcrum, and the heel lifts off. This heel lift or reaction force produced at the heel can potentially increase propulsion and thereby reduce the energy cost of running in these shoes, is what was proposed in that paper. But the problem was that the experimental evidence or results for this were not presented and not tested initially, and so we don't know how we would test this. So the purpose of the study 2 became to test methodologically whether we can analyze differences in the teeter-totter effect with different shoe constructions. To test this, we had 15 male recreational runners perform overground running at 3.9 meters per second in 2 shoe conditions. Now we have an AFT, which is the Vaporfly, and a flat control shoe, which is a Nike Air Force 1. And this was chosen to be able to eliminate any conditions that would allow a teeter-totter mechanism to happen when you're running. And we measured We measured plantar pressure data using the X sensor insoles, as well as high-speed video data using a Sony camera. And we were interested in calculating what's called a propulsion moment in this study as the indicator of a teeter-totter mechanism. The reason we chose this variable is because pilot data in an abstract published in 2021 showed that when you affect the construction of a shoe, you're able to affect the amount of reaction force in the rear part of the foot, as well as where it is located relative to that MTP axis. And so to be able to take into account differences in both of those variables, we calculate the propulsion moment. We only do this from 65 to 95% of stance because we don't want any influence of ground contact coming into the variable. And so all we want is to capture the reaction force due to the heel lift in the shoe. And we confirmed that this is from 65 to about 100% of stance through video analysis that we had. When we look at the propulsion moment on the y-axis here over 65 to 95% of stance in the two shoes tested, we find that the Vaporfly or the EFT in blue has a much higher propulsion moment compared to the control flat shoe in orange. And this was true for every participant, which you can see on the right is the integral of those curves on the left. And almost every participant had that reduction in propulsion moment when they went from an AFT to a flat control. And this difference was significant. So we've established that we can affect this variable that we've created, the propulsion moment, as an indicator of a teeter-totter effect, and we can affect that by changing the construction of shoes. So we can go back to our first purpose, which was to understand the effects of the two features on the teeter-totter mechanism. Based on all of the pilot data that we had and some of the suggested commentaries that were published, we hypothesized that removing the curved carbon fiber plate would reduce the amount of teeter-totter mechanism that a person experiences while running in these shoes, but replacing the PIBA with an EVA would not affect that. And the reason for this is because when the teeter-totter effect was proposed, the two main conditions required for it to take place were the curvature and the stiffness of the forefoot. And we don't affect either of those by changing the PIBA to the EVA. And we also hypothesized that the changes in the teeter-totter variable would also be associated with energy cost of running when we affect the plate. The methods were very similar to the first study where we had participants perform a baseline, determine their speed at lactate threshold, have them come in and run in the different shoe conditions in the same ABC CBA order. But the only difference now was that we included pressure insoles to test the teeter-totter variable. We calculated the same variable we've seen in the previous study. And what we find when we change the two different features is that by removing the plate in the Vaporfly, we're able to significantly reduce the propulsion moment by about 30% on average for all of these participants. The changes from the original to the EVA were not significant. There was no difference. As you can see, the lines are almost overlaid on top of each other, and that is exactly what we had hypothesized. So we hypothesized that we would change the teeter-totter variable by taking the plate out, and that this would relate to energy cost improvements. On the right here now, I have the energy cost on the y-axis and the propulsion moment on the x-axis. And we're trying to see the relationship between these two variables for each participant. And so this is an example here where we've plotted the no plate condition in triangles and original condition in the circle. And what you're seeing for this one participant is that when they go from a lower propulsion moment in the no plate to a larger propulsion moment in the original, they also go down on the y-axis. So there's a negative correlation for this one participant. And when we plot all 15, we see the same trend across most of the participants. The only one that went in the opposite direction was 1 out of the 15. And so from this study, we summarized that the teeter-totter effect is greater in shoes with curved carbon fiber plates, and that these changes might explain the improvements in shoes that use curved carbon fiber plates in their midsole. But this only explains what's going on with the curved plates. We still haven't answered the question about what's happening when we go from a PIBA midsole to an EVA. So we go to study 4, which looks at the effects of a curved carbon fiber plate and PIBA midsole on the lower limb joint work. Matijevich and co-authors in 2022 showed that advanced footwear technology construction has the potential of increasing the amount of work done by the foot and shoe complex in early and late stance phase. What this means is that the passive elastic structures and the compressive components of the shoe together can store and return more energy compared to a traditional shoe. If that is possible to effect with shoe construction, then we can expect some of that to be offset by needing less work at other joints like the MTP, ankle, knee, and hip joints. In fact, in a follow-up study, they even showed that the reduction or increase in the foot and footwear power that comes with an AFT construction is associated with a reduction in the work required at the ankle joint in those shoes. So based on this, we hypothesized that removing the curved carbon fiber plate in our study would reduce the amount of work coming from the foot and shoe complex. It would also increase the energy loss at the MTP joints based on previous studies that we've seen with flat carbon fiber plates, and that it would increase the amount of work required at the ankle joint. For the second modification, we hypothesized that there would be a similar reduction in the amount of work done by the foot and shoe. No changes at the MTP because the plate stays the same, but an increase in the amount of work required at the ankle joint. The methods were very similar to the previous studies, and so the only thing that is changing on this slide is the equipment that we use to measure the data. And so we had 3D motion capture and force platforms in this study to be able to compute the joint work and footwear work. When we go from the original shoe condition and remove the curved carbon fiber plate, we plotted the foot and footwear power here, which by taking the area under the negative and positive curves, we can get the work done by that foot and shoe complex in the two conditions. We find that there's a reduction of about 11% of how much energy or how much work is done in the first half of stance phase. And so the shoe and foot is probably storing a little bit less energy when you take that plate out of the shoe. That, based on Matijevich and co-authors' proposed mechanism, should relate to a reduction in how much energy can be returned in late stance phase, but we're not seeing that. But an interesting observation is that the energy return, the timing is actually shifted a little bit to the left. So it may be that without the plate, the shoe is returning that energy a little bit earlier, which may be less beneficial for performance. But what's happening at the MTP and ankle joints when we do reduce the amount of energy stored in that shoe? Well, at the MTP joint, we reduced or increased the amount of energy loss actually by 85% when we take the plate out. And the MTP joint also does about 40% less work without the curved carbon fiber plate in that shoe. And that translated to the ankle joint doing about 8% more work in late stance phase to push off. When we replaced the PIBA with the EVA in our second modification, we plotted the same foot and footwear power on this graph here. And what we find is that there's a 9% reduction in the amount of energy returned in late stance phase with the EVA compared to the PIBA. And this makes sense because the PIBA is actually more resilient. And so while it stores a lot, it also rebounds much better than an EVA to return all of that energy. Interestingly, in this modification, we did not really see anything changing at the MTP or the ankle joint. And even though these differences look like there might be something going on, the interesting fact here with the material changing is that different people react very differently. And so the range of reactions is quite different compared to the curved carbon fiber plate, where there's almost like a global effect of everyone reacting similarly. From this study, we summarized that the curved carbon fiber plate, I have two slides saying the same thing, so let's look at the nicer one. The curved carbon fiber plate reduces the amount of energy lost at the MTP joint, increases the amount of work done by the MTP joint in late stance phase, and reduces the amount needed at the ankle joint. And so there's a reduction in the energy loss as well as a redistribution of positive work. With the PIBA foam, the only difference we saw was greater energy return in late stance phase. So when we look at all of the studies that I did as part of my PhD thesis, we've answered some of the questions, like people were asking, what is the part of the shoe that makes it a good AFT? How much does the plate contribute to? How much does the PIBA contribute to? And we've answered some of those questions. And so according to me, what I speculate based on all of these results is that you combine a superior foam like a PIBA that returns more energy and probably does a few more things that we haven't been able to answer from these studies. You take a curved carbon fiber plate that increases teeter-totter effect, reduces energy loss, and reduces the amount of joint work required at the ankle. And you include a toe spring, which I speculate would increase teeter-totter effect and reduce the joint work required. You get a nice AFT like a Vaporfly. And even though we didn't test this variable here, this was too much to do for one PhD thesis. I think it's really important to look at the effect of the curvature of the shoe on all of these metrics. And if you were to ask me how much does each of these feature contribute to the performance improvements, I would say something about 2%, the curved carbon fiber plate, which is backed by the results that I found, 2% the superior PIBA foam, and then about 0.5% from the toe spring. And I know that math is more than 4%, a little bit more, but some abstracts that have come out recently have shown that the contribution of these together or the combination of these features might not add to the sum of them. And so there might be a little bit less contribution of them as a combination. And then I'd just like to thank my supervisory committee, Benno, Walter, my co-supervisor, and then my committee members, Darren and Jared. And then I would also like to thank all of the co-authors from the NIG group that helped with a lot of the papers in this thesis, and a lot of my peers at the HPL, but specifically Mike and Robin, because I go to them all the time when I'm confused what's going on with shoes and biomechanics. So thank you so much.
Thanks, Ashna. Does anybody have any questions to get us started? I'll ask a question. Yeah. So your muscle activation patterns, like from your first study, you found that there was no difference with the carbon fiber plate. Do you think that that's a consequence of the how fit the participants were? Like they were quite like more on the fitter side if they're able to run like a 10K in less than 44 minutes or whatever the cutoff was. Right. Would you expect that to be the case in recreational runners?
I think we might see a little bit more of a difference in recreational runners that goes more towards one direction. I think the elite aspect of it does have something to do with it, because the preferred movement path, which Benno has previously described, that people like to follow what feels best to their body, even if you change slight things in footwear conditions or surfaces. And so these changes are quite small, like you're taking one feature away from the shoe while keeping all of the others the same. So I think that could have something to do with it. But I also think the other aspect is there's a paper by, I'm forgetting the author's names, but there's a paper that shows that it takes about 7 to 8 minutes for people to start reacting in terms of muscle activation when it comes to changing minor things in shoes. And so that might be something, and I didn't pay attention to that paper before I did this study. So maybe the fact that it's so immediate that we're not seeing those changes could be another thing.
Any other questions? Yeah.
So I'm still trying to maybe connect the dots a little bit in terms of your muscle activation. If you showed that on average there aren't any differences, but you see the changes in metabolic cost. So now how does that relate to the other study that you mentioned that found differences in UG but did not measure metabolic cost? So I guess what's different between your study and their study? And then maybe another question could be what's going on in maybe other muscles aside from the ones you measure.
Right. I'll answer the first one first. So from the other study, the main difference is that they took the Vaporfly and a different traditional shoe, and they give no information on what this traditional shoe is and how it differs. The only piece of information we do know is that it does not have a PIBA and it does not have the plate. So that's one of the biggest differences, that the traditional shoe had none of the features that the Vaporfly has. So larger modifications from going from one to the other shoe, while my study had much smaller modifications. And then the other thing, I think both of our studies are actually underpowered to understand what's going on in terms of muscle activation. And the reason I say this is because I had 15 participants in my study, but the challenges with muscle activation measurements are that when they're there for an hour and a half doing those 6 different trials for 5 minutes with breaks in the middle, some sensors fall off, some sensors get really sweaty, and you lose a lot of data. So if you noticed, I only had about 10 and 11 participants for each of those muscles, where I had good data. And the other study that I'm talking about was actually published with 6 participants' data. So I wouldn't, bank on that result.
Okay, so then in general, you think that maybe it's still the same muscles that you recorded from, but just, let's say, less statistical power.
Right.
Or are there, I don't know, other findings that hint that maybe other muscles actually play a role into this as well?
Yeah, I think other muscles definitely would play a role. And I actually had the GM soleus PL and the tibialis anterior. Tibialis anterior and PL had absolutely no usable data for some reason. And so I was not able to understand what was going on those muscles. And I do think measuring more muscles even higher up would make some of the story make sense, because those are the bigger muscles, which I think would use more energetic cost than the smaller ones that we measured.
Tim?
Actually, I really enjoyed that. Thank you. That was really nicely done. And, I know when you showed your cases of the foot movement, it's kind of normalized the step cycle, but it's at the same time. But have you considered, or did you investigate, during the push-off phase, whether things are actually shifted so that the force velocity and where you're working on the force-length relationship are no longer the same with these different shoes, and that you might be at either slight disadvantage depending on how the rocking effect or how the flat shoe changes without those insoles. I'm just wondering if you're looking for a cost, it might be not other muscles over improving. There might be that the muscles you're using are not now in as good a situation to produce force for that.
So we did look at the timing aspect, and not well, I won't say not much, but nothing changed in terms of when these muscles were firing in the different shoe conditions. So not only the amplitude, but the timing was very similar across them. And the other thing that you mentioned was these are normalized to 100% of stance, but there were also no differences in ground contact in my study. So I found that ground contact was about 246 to 250 milliseconds for all 3 of these shoes. So I think I want to look into some of the timing aspects. Like for one of the graphs I mentioned, there was a shift in timing. I do want to dive deeper into that, which I haven't yet. But specifically for muscle activation, I didn't see anything.
Matt, you had a question?
Oh yeah, I was just gonna, first I'll start off by saying I really liked your slides.
Thank you.
Your graphs are really easy to see and clear. It's very nice. Can you just describe how you process the EMG signal? And what were the steps that went on there?
Yeah, so we didn't have force plates in the study. We had to use a heel accelerometer to take the vertical signal of that acceleration signal to be able to parse our steps. So we took the vertical acceleration to get heel strike, and then we got 300 milliseconds before and after heel strike first. Then we ran a root mean squared analysis to get the amplitude of the EMG signal, and then we calculated the area under the curve for those. Sorry, we also filtered the data before doing the RMS. And then, we got the curves, and then we calculated the area under the curve, which we then normalized all of those to the original condition to be able to make easier comparisons.
So all the EMG measurements are relative to the first condition. Also, it's all done in the same session with the same setup.
Exactly. And we didn't change where we placed the electrodes and stuff. Right. So they were placed on first, and all you changed was which shoe you were in while you were running.
And is there a reason why you chose to look at just like a 300 millisecond window in the area under the curve? Like, is there a reason why you didn't look at like peak EMG RMS, or maybe to the point like any sort of other features in the signal that? Because I imagine that window would depend, like a 300 millisecond window. I'm just trying to think ground contact time and running at 4 meters per second or whatever they were at. Would that have washed anything out, maybe? Or
so this is kind of, did I pop that up here? And don't take this as your specific example in terms of what's happening with muscle activation, because this is one subject, actually, not all of them. So just one subject, but here's what we have in terms of heel strike, and then plus and minus 300 milliseconds for one muscle. And then we take the area under the curve is just taken under minus 100 to plus 300 milliseconds, because that's kind of the functional window of these muscles that we tested. And I did look at different functional windows, so different timings where we go bigger window, smaller window. The results were not changing much. And the point you made about peak activation, I actually was not interested in peak activation specifically, because a lot can change during other parts of propulsion phase or stance phase. And if you only take the peak activation, I think you'd be washing out some of, or ignoring some of those results that could also affect the energy cost.
Well,
Online
actually, I got questions from online people. There are two. Question one, did you examine joint work more proximal to the body center of mass? Question number two, with the knowledge that you provide in your presentation plus literature, if you were to design a marathon shoe, which features would you prioritize?
The first question was work or joint work in proximal joints. And the answer to that is yes, we did measure the knee and the hip joint as well, and no differences were found at the knee and hip joint. So that's the first one. And then I'll go back to this slide where I will prioritize all three of these features in an optimal combination, which I can't answer yet because I didn't test a range of changing these features where I just either had the feature or did not have it. But in the future, I'd be really curious to see how changing the curvature of the plate affects performance, or the combination of that curvature of the plate and how much foam is below or above it. So I think I'd be really curious to see all of that. But based on this is my shoe for now.
Yeah, Frank.
I want to talk more about EMG. No, I just have a. Can you go to the EMG results?
The ones I showed or the ones I?
Yours that you measured, where it's like showing how it decreased or okay. So the top is original versus no plate, and the bottom is original. I'll agree with you that original versus EVA doesn't really seem like there's a consistent pattern. But I don't know, like the top one kind of looks like the large majority of people decreasing.
What about the ones that are in that red zone, which is the error of our measurement?
Yeah, but it's also EMG. So it's a terrible measurement to begin with. And
I agree.
I'm convincing myself that there's some kind of trend.
Okay.
But anyways, okay.
But let's go back to your trend. They're actually decreasing muscle activation in the no plate. So how do you explain reduced muscle activation but increased energetic cost?
In the no plate. Oh, okay, good call. All right.
Okay.
Yeah, I don't know. All right. Okay, so I'm trying to convince myself that what you call the teeter-totter effect is not just MTP joint work. So in my mind, if you have a more flexible shoe, you're going to absorb more energy at the MTP joint, which means more rotation is going to be taking place at the MTP joint, which means that measurement that you're making, there's just going to be less force on the other side of the fulcrum of the shoe. If that makes any sense.
Okay.
Like if the shoe doesn't bend at all, and your forefoot is sort of, I'm thinking of center of pressure of the forefoot, then there really shouldn't be any teeter-totter effect at all. It's just going to be equal and opposite to the force that your forefoot applies to the stiff, rigid plate. And then the more bendy you make that plate, the more rotation occurs, the more force you're going to measure on the. I'm not even going to call it a teeter-totter effect, because I don't know if I believe it yet. But what I do know in my mind is that the the less negative work taking place at the MTP joint, the greater that force is going to be at what you call the teeter-totter effect.
I get your
Tell me I'm
point.
wrong.
No, I get your point. And I think that the teeter-totter effect cannot be completely independent to any of these other measurements. Like, I think we've been measuring some part of that in all of these MTP joint work and moments that we calculate. But I think what it shows nicely is that because you're able to measure things using a pressure insole, and now you're measuring how much reaction force is generated just in that rear aspect of the foot, which you can't do when you're measuring on a ground on a force plate. I think that tells you a little bit more in depth on what is happening when you don't allow the shoe to bend here and the shoe's heel is lifting off the ground because of the construction.
How do you know that the force across the insole is just the exact same between the two different shoes, but the more flexible shoe has a center of pressure that's further back towards the heel, which means that there's just more force back there. And so it's not a reaction propulsive force per se at all. I mean, it is at the end of the day, I guess, because it's during the propulsion phase of stance, but it could just be that the applied force is the exact same between the two divisions.
Well, I'm showing the propulsion moment, which is now combining the two, but we looked at each individually. And initially, we were just looking at the amount of force because when Benno proposed this, it was just that there would be a larger reaction force in the rear aspect of the foot. But then we also saw that that's bigger, but also further back. And so that's why we did that. But I wouldn't say that result was influenced by one being more and the other not changing at all. It was a change in both of them. Like, we can talk about the plots maybe some other time too.
So a change in the location, but also the magnitude of the
Correct.
But the magnitude of the force where you measure it in the back,
Yes.
not the total magnitude of force on the entire
No.
Pressure.
No. The distribution changed.
The distribution changed.
Yes. Yes.
Other questions?
Just to clarify, these running speeds are constant, right? These are running the constant speed, even speed.
The overground measurements, yes, they're running at 3.9 meters per second. On treadmill, they're running at 90% of their speed at lactate threshold. So it's a constant relative intensity.
And then you said knee joint and hip joint are same joint work, but MTP and ankle are changing. And at the end of the day, ankle is doing less work, mechanical work. And my question is, if the speed is constant, there is no acceleration. If there is some work that is less positive, then there should be some acceleration on this system, but there is not. What's the mechanism behind this?
I don't think I would say there's no acceleration. The speed is constant by taking the measurements from the timing gates, but we don't control for the acceleration and deceleration, right? I can make that comment if I checked the ratio of the anterior posterior force from the ground reaction forces, but I didn't do that. So we only controlled for the speed, not the acceleration and deceleration.
But treadmill, how about treadmill?
The joint work was done over ground because the Bertec was not working at the time.
And then did they begin from 0 speed, or did they have a steady speed when they passed the timing light?
Well, I would hope they had a steady speed when they passed the timing lights, but they did start from rest in the main lab and then had a 5-meter distance where
the
timing
section
lights.
that you measure with the motion capture and force place where they should be having roughly constant speed, right? But then my question is still valid. So you have zero acceleration, roughly zero, and you have some excessive positive work. They should be absorbed somewhere, so they have zero acceleration. If there is some more work, positive work done on a system, human or anything, if you don't take care of it, then you accelerate. F is equal to ma. If a is 0.
So I think they would accelerate. Like, okay, so this is a tough one to answer, but I think they would accelerate had we not controlled for it. Had we said run your normal
I
speed.
understand
but
the accelerate from
and
pure
I-
speed, yes.
Right. I understand your question, but also there's not just an increase in the ankle work, there's also redistribution. So there's less being done at the MTP in one condition and more at the ankle, while in the other condition, there's more work that comes from the MTP joint. And so maybe the ankle has to do a little bit less.
Then this affects, there is a mismatch between the metabolic and mechanical aspects then. I'm not saying how shoe is reducing the metabolic work.
Not sure if I have the answer
Okay,
to that question.
I believe in that. MTP and ankle are sharing the work differently.
Right.
And you said knee and hip aren't different.
Mhm.
Okay, so mechanics and metabolics should be matching each other, right? Probably. But we are not sure right now whether shoe is doing something. Maybe it is.
Mhm.
But the effects, I'm not linking the effects, mechanical effects to the metabolic energy expenditure right now from the data. Load sharing is an example, but
Right.
Yeah, it may be the reason, but okay.
Yeah, I see your point for sure, but I don't have an exact answer to
I
it
think
yet.
I asked the same
Arash, you had
question.
a
Brand
question?
asked in a different way. You know, he's more in the details, how the moments and forces change, and if you look at the whole body, then it's acceleration values.
All right. Arash, you had a question?
Actually, I have more of a comment on the teeter-totter effect, and the fact that I think, like thinking about two kids being on the teeter-totter, the effect with the angular acceleration. What you would see is going to be angular acceleration increase in the rear foot, and you can actually calculate that. Using even inverse dynamics, you can actually go back and calculate that number and see if there's a difference. So if you do like a pressure insole inside the shoe, you probably won't find any specific number difference in the pressure or force, but the angular acceleration would be highest. So if you go back to your data, you should be able to actually calculate that. Some sort of an IMU in there and see if there's a difference. So it's exactly provable if the effect is a teeter-totter effect. Like two kids, one kid is sitting here and the other kid is going up. Then what's happening is actually what you will be able to measure is going to be the motion, not the strength. Because again, you're moving. So the F equals ma eventually ends up the acceleration, not the force.
And in your, if I could just talk, and in your mind, would that increase angular acceleration potentially change the contact time of the foot with the ground? If you increase the angular acceleration, did you get off of your foot faster?
I think so.
And you have no changes in ground contact time.
No.
And also, that increase in angular acceleration is if you put the equations in the inverse dynamic equation, at the moment for the ankle, for example, is not going to be much affected by that angular acceleration.
Does anybody have any questions for Ashna? So we can probe at her expertise.
Come on.
Yeah.
So going to your result, you found a positive influence of the stiff leg. And then in your intro, you referenced your grandma a lot. And he did a very similar study where he removed this. He didn't remove it, but he cut the stiff leg. And he found no effect. And he attributed all the positive effects of the Vaporfly to cushioning. So why do you think you found an effect there, where in his study he did not?
First thing, I think cutting the plate versus taking it out would have a little bit of influence, although they did show stiffness measurements and they did reduce the stiffness substantially. But also their p-value was super close to significance, and they had 11 or 12 out of 15 people that actually had a worsening of energetic cost, even up to 3.3%. And so I think, and I ran a power analysis because I'm writing a discussion for my thesis right now, and they were a little bit underpowered. So I'm almost skeptical that it could have been statistically significant. And I wouldn't say that they didn't find any differences at all, considering so many of the participants had a worsening. And then they also did an abstract after, presented at FBS, which they removed the curved plate and did find about a 1.3% reduction in the energy cost, or increase in energy cost.
Jared, do you have a question?
So I'll spin that question on the data you're showing right here, where it looks like in the GM intensity difference, you have 11 of 12 people that went down. What's your power to say that they're not different?
Yeah, I can't be sure. So with my EMG results, my main answer right now is I don't know what's going on in terms of EMG, and I wouldn't call most of my results conclusive in any sense. One, just having two muscles in there. Two, the error being quite large, where a lot of these participants are landing into that error, even though they're showing that trend of moving. So I completely agree to the limitations in this study, where potentially I was underpowered. This was showing some sort of trends. The only thing that boggles my mind is why are they all reducing muscle activation and increasing energetic costs? I'd love an answer.
You have an online question, Hala?
Yeah, we got a question online. Walter, go ahead.
All right, yeah, can you hear me, Ashna? Hello,
Just one
can you
second.
hear me? Is
Go
this
ahead.
good, Juan? Yeah, can you hear me?
All good. Yes.
Okay, great, yeah, thanks a lot, Ashna, very, very clear talk, I really enjoyed that. I have a few questions. The first one, I guess, is when you, I think it was when you talked about the teeter-totter experiments, you showed the results only for 65 to 95% of the stance phase. So what happens at the beginning of the stance phase in the first 65%?
Why I don't show those results is because the rear aspect of the foot, which is where we're calculating the teeter-totter force, is actually still touching the ground. So you're still in that early and mid stance phase, right up till about 65% of stance, where we saw from video data that that's when none of the rear aspect of the foot is touching the ground anymore. So that's why I don't include that. And all I'm interested in is what the force is when the foot doesn't touch the ground. And so we're calling it a reaction force that's coming from the shoe onto the runner.
Could it be that in that first 65% of the stance phase, you might actually have a disadvantage with the teeter-totter that then comes out as an advantage in the last part? Or do you think there's an overall improvement and the first part really doesn't matter?
I'm not sure if I understand what a disadvantage would mean in the first half.
Well, when I see the teeter-totter, it almost reminds me of that you have to go uphill first and then you go downhill. You know, you go over that teeter-totter and it takes work to get on there, and then you get free work once you're over the hump. And so I was just wondering what it, you know, what that would be. But obviously you didn't measure that, so there's not really an answer there. The other thing is when you calculate joint work, I assume you're doing the inverse dynamics and then you have the resultant moment, and you really don't know, you really don't account for possible co-activation or joint moments produced by two joint muscles. Is that correct?
Yes.
Yeah. So your joint moment could be lower, but the work done by the muscles, if you have more co-contraction, for example, could potentially be higher.
Right.
The other thing that I didn't quite understand is when you showed that EMG, you know, you showed that you do an integration of the EMG.
Mm-hmm.
Yeah, but the EMG that you showed, the example that you showed, is an EMG that goes up and down. But if you integrate over a certain amount of time, and you have presumably a full wave rectified EMG, then I would expect the EMG to increase. It never will come down to zero. So I didn't quite understand what you did there.
Let me just pull up that graph, Walter, so we can walk through it. Is this the one you mean?
Yes, exactly. Yeah. So,
Right,
there,
and you mean that.
you
Mhm.
seem to be showing there that you make an integration from T1 to T2. And if there's always an EMG there and you full wave rectified it, then I would assume the EMG will go up, 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 up. It will never come down.
Hmm.
I think what you might have done there is what people call a linear envelope, that you smoothed the full wave rectified signal and then approximated it with some kind of a smooth line. But I don't think you actually did an integration of calculating an area under the curve of a full wave rectified EMG.
So we calculated the root mean squared using a sliding window approach, and that smooths the curve. And then we take the area under the curve that we get from the RMS sliding window approach. So is that different from what you're saying, or?
Well, what I'm saying is,
You're showing
what
the
I'm saying-
integration of a time series, but you're not showing the integration.
Oh, I see what
That's
you
why
mean.
he's wondering why it's
I
going
think
down.
your
Oh, this
equation
is.
doesn't your equation doesn't seem to show what your graph is showing.
So the graph is the actual RMS, like the smooth signal once we perform the RMS, and then the shaded area is what I mean as the area under the curve. And then that comes out to one number. So let's say 0.89 or something. And that's the overall intensity during that functional window that represents how much muscle activation was in that shoe.
And it seemed at the beginning of your talk, on one slide, you seem to be talking about energy, but the units seem to be watts. I'm not sure if that was your mistake, or if that was the mistake in the original paper that you showed there.
Is it this one?
I think it was a newcomer paper there at the beginning.
I may have labeled the y-axis. Well, they call it metabolic power, so that's why they call it watts per kilogram. And I called that energy cost on my slide while labeling it. So would metabolic power be the correct thing?
Well, I'm not sure what
the
right thing is, because I don't know what they measured, but I
Right.
see energy and then I see watts, and I'm going, there's something not quite right there. But
right.
But it's for you. I don't know what was measured, so I cannot really say what the right.
Right.
So did you do this with forefoot and rear foot strikers?
Just rear foot strikers.
Do you think there would be a difference with forefoot strikers, particularly is the teeter-totter effect?
I think yes, in the teeter-totter effect specifically, yes, because I think you need to land on your rear to mid foot and then transition towards the forefoot to actually benefit from that teeter-totter motion. So actually this goes back to what you were saying, where you almost need to have that first bit of loading to be able to get the return of the teeter-totter. So I think if you're going into forefoot running, that mechanism might be less beneficial.
I'm more of a midfoot, forefoot striker, and when I ran in the Vaporfly at Nike, my improvement was 3.8%. So in terms of energy cost, so I am a forefoot striker, and it seemed to give about the same as the average of other people, which I thought was interesting. And just the last thing, so people are interested not really in how much energy they save or how much less metabolic or how much less oxygen they need to uptake, but they are interested in how much faster they run. So have you thought about what that might mean? I'm putting the Vaporfly on, I have 4% less oxygen for running at a certain speed. How much faster am I going to be able to run a 10K or a marathon?
So I think there is a paper on this that has shown, I think it's by Kip and Cram, and they showed an equation that you can use to calculate how fast you would run with certain metabolic energy savings. And so I believe a 4% saving translates to about a 3.3 or 3.4% faster race time based on that equation.
Okay. And do you know anything about track shoes that people are wearing now? Because people are not only getting faster on the road, but they're getting super fast on the track as well. I assume, therefore, that some of this technology has also been implemented in track shoes. Is that correct?
Yes, that's right. I believe a lot of plates are being used in track shoes these days as well.
But not the thick soles, presumably.
No, from my knowledge, no, but I could be wrong.
Yeah. No, I was just wondering because I know in the Vaporfly feels a bit unstable, and I was wondering how you negotiate hurdling, let's say like in a steeplechase or in the 400-meter hurdles, if you had a relatively wobbly, unstable shoe. So great, thank you.
Thank you, Walter.
All right, any last questions, Matt?
Sorry, I'll just beat this dead horse one more time. But those, I'm still just struggling with the EMG processing.
Same.
And,
I'm struggling.
Yeah, and the reason is, Ashna, is like, let's say I'm looking at jumping, and I have quad, hamstring, and calf. And like it's pretty clear, like you have low grade activity in your muscles that are happening, but then when you look at the sequence of how EMG activities go, which you've done with your RMS, right? So you've created a measure of the amplitude. The timing and the peaks really do sort of correspond to where the muscle groups are really mostly involved in that movement. And it's not 300 milliseconds where the plantar flexor would be involved. It would be a very brief instance of that whole kinetic chain where the plantar flexor is optimal to do what it needs to do. And I think about it two ways. The first thing is I think that maybe it washes things out and the peaks do sort of show something. Like even when I look at the representative graph you give, I can see that the area is the same, but the peaks are quite different and they're differently shaped. And I also wonder if that's a bit of a red herring, like maybe the plantar flexors are put into a better position to generate muscle force and torque. You're optimizing other things. So the idea of, washing it out with your average analysis in that whole area, where it just sort of like bleeds it out, the result. Do you have any comments on that? Or do you think it's, I know you didn't want to look at the peaks, but
Now I do.
do you think it might be something? Because to me, I would be really interested in that. Jumping,
Yeah.
you see it. It's like peaks happen in different muscle groups, and they really do correspond to different phases of the movement.
Right.
And if I was to like look at an area, it would probably just miss things because of those tails.
No, that's a great suggestion, and I think I'll take a look at that as well as I
Interesting.
write the discussion of this, but
Who knows?
I'll definitely look at it and maybe circle back on that. Yeah, thank you.
Colin, you had a question?
Ashna, props on getting through your first mini issue defense right now. And my question is more about, you looked at all these different features, but I think the one that's missing is weight. I'm just curious what you think the effect of just overall shoe weight would be when you have this thing, swinging at the end of a chain essentially, and would that be greater than the effect of all these other things? And then did you also try and normalize that when you're creating EVA shoe, which I'm also super curious on how you even did that.
Yeah. So we started by weighing the shoes to see if we needed to weight match, and the largest difference was between the original and the EVA, which was only about 23 grams. So we did not weight match because there is a lot of studies that have shown the effect of shoe mass on running energetics, and so it's pretty established that every 100 grams of mass you add to each shoe is when you're increasing 1% of your energy cost. And so yeah, I think that's the main reason we didn't need to test it or address that in our paper.
Do you think we should just be making the lightest shoes possible and like, regardless of everything else, just focus on that, or do you think it's just still a combo of everything?
So I think the lightest shoe possible is not, like, I think that paper that shows the effect of shoe mass also shows that there's a sort of a threshold where it just stops improving energy cost. I think it's below 200 and, or I can't remember what exactly the shoe mass is, but below that you stop getting energy improvements. And so I don't think that's it, but I think striking the balance between having a lightweight shoe while also combining all of these other features that we're getting. So people are trying to add thick midsoles, but then you might increase the weight a lot. And so you want to choose the right material. So I definitely think the shoe mass has a lot to do with it and should be kept in mind when incorporating a lot of these features into the shoe.
Awesome. So
Really,
let's think.
really quick, really quick.
Okay.
I seem to remember that you also did something to these shoes to change the toe spring,
Yes.
but you didn't show us any of those data.
Here. For which variable
Really
specific?
quick. No, I don't trying to see anything, but what did it do?
That's the shoe Brent was
Right,
talking about,
Yeah.
the clown shoe. But which do you have a specific variable in mind, or just any and
What did it do
everything?
to the metabolic cost?
So we did not include this shoe here is because that was the only thing we could not measure in this shoe. Having people run on a treadmill in this shoe was safety hazard, and so we couldn't determine the metabolic cost. And also the fact that we didn't really affect the toe spring as we had intended to, because this toe spring is, or toe wedge is made of the same PIBA foam that was harvested from the EVA condition. And so it's so squishy that people almost entirely squish it in late stand phase. And so it didn't really do what we wanted it to do. It increased the ankle joint work that was required in this shoe. That was the only big change.
One more thing.
Oh, no, okay. Well, let's thank Ashna again.